All right, hello everyone. Today we're going to be going over section 5.1, which is about the product rule and the power rules for exponents. So we have 5 objectives here. Our first objective is to use exponents. Our second objective is to use the product rule for exponents. Our third objective is to use the rule a to the power of m all to the power of n is equal to a to the power of m times n. Use the rule a times b in parentheses all raised to the power of m is equal to a to the power of m times b to the power of m. And then for number 5, we want to use combinations of the rules for exponents. So objective 1, we want to use exponents. And we can recall that we write exponents as repeated products. So in something like 5 to the power of 2, 5 is the base and 2 is the exponent or the power. The expression 5 squared, or 5 to the power of 2, is an exponential expression. So if we have something like 3 times 3 times 3 times 3 times 3, we see that's going to be 5 3's that are being multiplied by each other. This is not the same as 5 times 3 because we have 5 factors of 3 all being multiplied together. And when we write that, we want to write that as 3 to the power of 5. And this is in our exponential form. So a word of caution in cases like -5 to the power of 4, where your negative is just outside of the base and there are no parentheses involved. This absence of parentheses indicates that the exponent 4 applies only to the base of 5 and not actually -5. If it applies only to the base of 5, then this means that you'll take 5 to the power of 4 like normal, and then your negative sign will just be included in your final answer. The negative sign is then being included to the final answer, and you're not multiplying out -5 to the power of 4. In the case where you do have -5 with parentheses around it to the power of 4, the parentheses indicate that the 4 does apply to the -5. So in that case, you would multiply out -5 4 times. So when we see expressions written as -a to the power of n, where we have no parentheses, the base is recognized as just a, the exponent is n. And so a certain example would be -3 to the power of 2 is going to be -3 times 3, so we're going to end up with -9. But when we have parentheses around our negative number, so if we have parentheses around -a all to the power of n, our base is now recognized as -a, where our exponent is still n. So now if we have -3 in parentheses to the power of 2, we have -3 times -3, which is equal to +9. So it's really a key difference there, and it's really important to look out for when you're working through problems. All right. Objective 2, we want to use the product rule for exponents. So a helpful example to introduce our product rule would be something like if we had 6 to the power of 2 times 6 to the power of 3. 6 to the power of 2 can be written as 6 times 6, while 6 to the power of 3 can be written out as 6 times 6 times 6. So really what we have here is we have 6 times 6 times 6 times 6 times 6. So once we have all of these values, we can drop our parentheses because they're not doing anything at this point. And once we do that, we see that we have 5 factors of 6, which would make this exponent 6 to the power of 5. So we're introducing this fact that 6 to the power of 2 times 6 to the power of 3 can be written just as 6 to the power of 2 plus 3. So we can just add our exponents to get our final answer, which is 6 to the power of 5. This suggests the product rule for exponents. Our product rule for exponents says that for any positive integers m and n, so these are positive exponents, a to the power of m times a to the power of n is equal to a to the power of m plus n. So really we're thinking about numbers that have the same base but different exponents, and when we're multiplying them together, we add their exponents. We want to keep the same base and just add exponents. So for example, 6 to the power of 2 times 6 to the power of 5 is the same as saying 6 to the power of 2 plus 5, which is 6 to the power of 7. So a word of caution, when using the product rule, keep the same base and add exponents. you don't multiply the base. So 6 to the power of 2 times 6 to the power of 5 is equal to 6 to the power of 7, and it's not 36 to the power of 7. So you're only adding exponents. You're not doing anything to the base. The base is going to stay the exact same. You're not multiplying the base because that would give you a completely different answer. So only adding exponents. And we can go ahead and put this into a little bit of practice. So we want to use the product rule, and we have m to the power of 2 times m to the power of 5 times m to the power of 9. So let's go ahead and just kind of color code our different exponents here, and then we'll write them out. So m to the power of 2 can be written as m times m. And what we have here indicated is m to the power of 2. Then m times 5 can be written as m times m times m times m times m. This is to the power of 5, so we have 5 factors of m. And now we're multiplying by m to the power of 9. So we're going to have quite a few m's here. There we go. 9 factors of m now. So we've multiplied out, instead of having them written as exponents, we've written them out and we've really shown what they look like when we multiply them all together. And now we can go ahead and we can count all of our m's that we have. So we have 2 m's here, which we know. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16. So there's 16 m's here. The same thing we can solve if we just took m to the power of 2 plus 5 plus 9. And this will give us the same answer, m to the power of 16. So whether you want to expand out your exponents, you can go ahead and do that if that makes it easier, and then just count them all individually. But our product rule does state that we can just add our exponents if we have the same base. So our m to the power of 2 times m to the power of 5 times m to the power of 9 just becomes m to the power of 2 plus 5 plus 9, which will give us m to the power of 16. All right, so another word of caution, note the important difference between adding and multiplying exponential expressions. If we have something like 8x to the third plus 5x to the third, this is going to mean 8 plus 5 in parentheses times x to the power of 3, which is 13x to the power of 3. If we have 8x to the power of 3 times 5x to the power of 3, this is going to mean 8 times 5 times x to the power of 3 plus 3, which is then going to equal 40x to the power of 6. So there's really that difference between adding and multiplying. When you're adding, you're really just adding the coefficients because the exponent for the variable isn't going to change at all. But when you're multiplying, you will add those exponents for your variable, and then you will also multiply your base if they're different. If they are the same, then you wouldn't do that, but if the bases are different, you will have to multiply them. All right. Objective 3, I want to use the rule a to the power of m to the power of n is equal to a to the power of m times n. So another helpful example, really what we're looking at is we're looking at a number that has an exponent, but now we're raising it to another exponent. So in this case here, of 4 to the power of 3 to the power of 4, our base is going to be treated as 4 to the power of 3. This is our base. And even though our base has an exponent, we're treating the whole thing like the base. And our exponent now is 4. So we're taking our base, or what we recognize as our base, which is going to be 4/3, and we multiply it out 4 times. Then what we see we end up with is this 4 to the power of 3 plus 3 plus 3 plus 3, which is going to be 4 to the power of 12. So we could just multiply those exponents from the get-go instead of adding them all from what we learned in our product rule from our last objective. So now we have 4 to the power of 3 all to the power of 4 is equal to 4 to the power of 3 times 4, which is just equal to 4 to the power of 12. This suggests the power rule A for exponents. So we're going to have a few different power rules, but this is our first rule, so it's going to be power rule A. And our power rule A states that for any positive integers m and n, a to the power of m, which is also raised to the power of n, is equal to a to the power of m times n. So you raise a power to a power by multiplying exponents. So, for example, 3/4 to the power of 2 is going to be the same as saying 3 to the power of 4 times 2, which is just equal to 3 to the power of 8. So we can go ahead and do a problem on this as well. So example 2, we want to use power rule A to simplify 5 to the power of 7, also to the power of 2. So this is like saying 5 to the power of 7 times 5 to the power of 7. 2 was our exponent, 7 was our exponent, 2 are to 5, but we're treating 5 to the power of 7 as our base. Which, just like before, this is like saying 5 to the power of 7 plus 7. We got this from our product rule, but from power rule A, we get that this is the same as 5 to the power of 7 times 2, which is going to give us 5 to the power of 14. So whenever we have power raised to another power, we're going to multiply those exponents. Now, objective 4, we want to use the rule a times b to the power of m is equal to a to the power of m times b to the power of m. So now if we have two separate bases, or two numbers within our base, and raised to an exponent, we can separate out those two terms in our base by our exponent. So we would distribute that exponent to both numbers in our base. So another helpful example before we introduce our next power rule would be if we had something like 4x to the power of 3. So our 4x in this case is once again our base. But we can also have this as a times b. So 4x to the power of 3, we can rewrite that as 4x times 4x times 4x, which we can then rewrite. Since it's just multiplying, we can rearrange them any way we want. So we can rearrange this to say 4 times 4 times 4 times x times x times x. Or since we have 3 factors of 4 and 3 factors of x, this can just become 4 to the power of 3 times x to the power of 3. Now we can leave our answer in this form, this 4 to the power of 3 times x to the power of 3. We obviously don't know what x is, so we would leave x as x to the power of something. But 4 to the power of 3, we can actually find that value. It would just be 4 times 4 times 4. 4 times 4 is 16, and 16 times 4 is 64. So our final answer in this case will be 64 times x to the power of 3. A lot of the times you will have a coefficient or some number to a power, where if it's not a variable, you most of the time do want to solve for that value. So now where we had 4x to the power of 3, we're saying that this is equal to 4 to the power of 3 times x to the power of 3, which is suggested in our objective name. Then we can simplify down to 64 times x to the power of 3. And this is suggesting our power rule B for exponents, where power rule B is going to be for any positive integer m, a times b to the power of m is just equal to a to the power of m times b to the power of m. So we're raising a product to a power by raising each factor to the power. So in another example, 2 to the power, 2 times p to the power of 5 is the same as 2 to the power of 5 times p to the power of 5. All right, so example 3. Now we want to use the power rule b to simplify 3xy to the power of 2. So 3xy to the power of 2 is the same as saying 3xy times 3xy, which we can once again just rearrange as 3 times x times y times y. So in this case, we have 2 factors of 3, 2 factors of x, and 2 factors of y. So this will end up being 3 to the power of 2 times x to the power of 2 times y to the power of 2. So we've successfully now distributed our power to each factor of our base. We can take this one step further. 3 to the power of 2 is going to be 9. So we can write this again as 9 times x squared y squared. So another word of caution, power rule B does not apply to a sum. If you have 4x to the power of 2, this is going to be equal to 4 to the power of 2 times x to the power of 2. But 4 plus x to the power of 2 is not equal to 4 squared plus x squared. They are not equal. So if you have a sum written in your base and it is not a constant plus a constant, if it is a constant plus a variable, it's not going to be the same as saying 4 squared plus x squared. It has to be some number times another number or just a simplified value, like a simplified constant in your base. So from power rules A and B, we can also generalize power rule C for exponents as well. So power rule C is now telling us that for any positive integer m, if we have a fraction, a divided by b, all to the power of m, this can also be rewritten as a to the power of m divided by b to the power of m, where b doesn't equal 0. We raise a quotient to a power by raising both numerator and denominator by that power. So in an example, something like 5/3 to the power of 2 can be written as 5 squared divided by 3 squared. So you're distributing your exponent to both your numerator and your denominator. And here is a summary of our power rules for exponents. Our rules for exponents we have for positive integers m and n, the following holds true. The product rule, where we had a to the power of m times a to the power of n, is written as a to the power of m plus n. Examples would be something like 6 to the power of 2 times 5 times 6 to the power of 5 is equal to 6 to the power of 2 plus 5, which is 6 to the power of 7. Then our power rules A through C. Power rules A tells us a to the power of m times n. A to the power of m to the power of n is equal to a times a to the power of m times n. So an example of that would be 3 to the power of 4 to the power of 2 is the same as saying 3 to the power of 4 times 2, which is 3 to the power of 8. Then power rule B, we have a times b to the power of m can be written as a to the power of m times b to the power of m. Something like 2 times p to the power of 5 is equal to 2 to the power of 5 times p to the power of 5. And lastly, power rule C, if we have something like a divided by b all to the power of m, can be written as a to the power of m divided by b to the power of m, where b is not equal to 0. So in any case, we would have, if we had something like 5 divided by 3 all to the power of 2, that could be written as 5 to the power of 2 divided by 3 to the power of 2. Objective 5, we want to use combinations of the rules for exponents. So example 4, we want to simplify the expression. We have 1/2 x to the power of 4 times 1/2 x to the power of 2. If we want to go ahead and we want to do some labeling, we can say that a is going to be equal to 1/2 x. In this case, it would turn our problem here into a to the power of 4 times a to the power of 2, where we know from our product rule this is equal to a to the power of 4 plus 2, which is equal to a to the power of 6. So now, plugging 1/2 x back into a to the power of 6, we're going to get 1/2 x to the power of 6. And we want to continue simplifying. So now we can state that maybe a is 1/2 and b is x. So now we're saying a times b to the power of 6. And this is going to give us power rule b, since we have a times b to a power. Where we know by power rule b, we can write this as a to the power of 6 times b to the power of 6. So then a to the power of 6 times b to the power of 6 is going to give us 1/2 to the power of 6 times x to the power of 6. So x to the power of 6 is now simplified. So really what we're looking at is we have a 1/2 to the power of 6 times x to the power of 6. Well, we have a 1/2 to the power of 6. We have a fraction to a power. So we want to simplify this one more time. We're going to say that a is equal to 1 and b is equal to 2, where now we have a divided by b to the power of 6 times x to the power of 6. And this is our power rule C. And our power rule C, from this, we know we're going to get a to the power of 6 divided by b to the power of 6 times x to the power of 6, where now we can plug these values back in, 6, to get 1 to the power of 6 divided by 2 to the power of 6 times x to the power of 6. Now I just want to simplify as much as possible. So 1 to any power is just going to be 1. So we really have 1 divided by 2 to the power of 6 times x to the power of 6, where we can find 2 to the power of 6. And it's going to give us 1 divided by 64 times x to the power of 6. So this is in our most simplified form. We've simplified our constants that had exponents, and we simplified with our variable, which now has an exponent. So, all right, that concludes section 5.1. So I'll see you again in section 5.2.